Okay. Well, I'm very pleased and honored and privileged and all those things that we say about great people when they come here to speak to us, to introduce Professor Robert Howarth, who is today's colloquium speaker. Dr. Howarth is the Atkinson, or the David R. Atkinson Professor of Ecology and Environmental Biology at Cornell University, where he's been at Cornell since 1985. Now, I have known about Professor Howarth's work since I was a graduate student, and actually he was a graduate student. He started out working on sulfur cycling in salt marshes and did some extremely innovative and influential work in the area of sulfur cycle during the 70s, changing some of the way we looked at the nature of that cycle in sediments. And so he's extremely influential in that regard. And he's continued to be influential in fundamental, what we call fundamental basic science of elemental cycling. In particular, gone on to work extensively in the nitrogen cycle on multiple scales, regional scales, global scales. And he's progressively, over his career, emphasized how human beings have come to emphasize, to influence the environment of the planet and some of the implications of those influences for us. He's also become increasingly involved in aspects of energy policy, energy usage, and how it influences environmental processes. And so just to give you a little background on his education, he actually grew up in New Hampshire, rural New Hampshire. He is a product of public school systems, which is nice to hear on occasion. Yeah, there you go. We have one here.
From New Hampshire, yes.
Yeah, from New Hampshire.
And
they continue to influence our political systems disproportionately, I might add, just as some of them disproportionately influence our science, as you have, Bob. He, in addition to being at Cornell, he is at the Ecosystem Center at the MBL in Woods Hole. He's done a whole slew of services for our community, including being the founding editor of the journal Biogeochemistry, which many of us read and are familiar with. And he was instrumental in getting that journal off the ground and making it a world-class journal in that area. He's also served extensively as consultants for different governmental agencies, really too numerous to mention, and that's what happens when you're too famous. We don't even say anything because you're so famous we can't list everything that you've done. He's worked on the Exxon oil spill in Alaska, and he continues to be involved in climate change. And I see here that he was given honorable mention as one of the 50 people on Earth who matter. I love that because that means that people like me is one of the 7 billion who don't matter.
Who decided? Where'd that list come from?
I'll show you a slide.
This is what I
get an email every day to be included.
There you go. I'm just kidding. I'm not kidding about mattering because he does matter. So, on many different things. Today, that's right. Today he's going to talk to us about some of the most contentious issues that we presently have in New York, as well as in the United States, with respect to fracking and shale gas usage. And so I'm very pleased to welcome you, Bob, and
Thank you.
have fun.
Thank you, Bob.
Exxon is monitoring this talk.
Well, that's true to begin with, but can you hear me if I don't use this microphone? Because when I try to
There's
hear
a fan that goes on. No, there's a fan that goes on.
so is it going to do it? Can you hear me now?
Yeah, you can. I'll put it on.
Someone control me.
Is that okay in the back?
Can you hear me?
Yeah, that's
Okay.
Turn it down even a little more. Okay.
Thank you all for coming today, and thank you, Bob, for that incredibly flattering introduction. That's the most flattering introduction I've ever had. So I'm honored to be here. I'm going to talk about some of the science we've been doing on this issue of fracking, concentrating on greenhouse gas emissions. I'll talk a little bit about other aspects of it and a little bit about the politics as it goes along, just because I can't help myself. It is true that if this will go up in the web, I'm told, it is true it'll be monitored by those in industry. And so anything you say in the question and answer period will be monitored by industry. Just be warned. But they will have a little piece posted on the website within a few days after this goes up as to why what I say today is wrong. If you want to get the other side, it'll be up soon. I press this, huh?
Maybe.
There, okay. For those of you, most of you probably haven't thought a lot about what shale gas is and is not, so just bear with me for a second by way of general introduction. This is a very, very simple schematic, but it's from the US Department of Energy. And conventional natural gas is methane that has diffused over geological time in a permeable basin of some sort, like sandstone, capped by some sort of impermeable geological formation. And all you do simply is put a pipe down into that, it's pressurized, you get to the surface. That's conventional gas as it occurred 100 years ago. Now, conventional gas over the last 30, 40, 50 years has been augmented by this process called hydraulic fracturing, where industry puts water under pressure in there to sort of boost up the formation and displace some of the gas. The reason I mention that is that industry will tell you fracking, hydraulic fracturing, has been around for 50 to 60 years. That's absolutely right. Classically, they'd put in 10,000, maybe 50,000, up to 100,000 gallons of water to do that. None of that comes back to the surface. It sticks in this permeable basin. Now, shale gas is the gas that is very, very tightly held in a shale formation. It's just not extractable by the classical techniques. And what has allowed it to become developed is a combination of two technologies. One is high precision directional drilling, so they can drill down, find the shale formation, and then follow along. And they can do this within a meter or two. It's really incredible. So a shale gas formation that might only be 50 meters thick, they can follow along and they can put out wells for up to 2, 3, 4 kilometers in that small little band. And then they blast the hell out of it with water and other fluids, hydraulically fracturing. Typically now they use about 5 million gallons. And of that, 1 million to 2 million gallons comes right back to the surface in a time period of a week or two, right on. So there are a lot of issues associated with that. I'm going to talk not too much about the water quality issues, hardly at all. Again, the greenhouse gas. I want to emphasize that this technology is new. And what this shows is from January of 2006 to the present, 2008 to the present, the rate of shale gas development in the United States by the various fields where it's been developed, mostly in Texas and Louisiana, only recently elsewhere. There was nothing if you go back 12 years ago. Half of all the shale gas that's ever been developed on Earth has been developed in the last 2.5, 3 years. Very new technology, all in the United States. There's a little bit in Canada now, there's nothing going on anywhere else in the world so far. So it's new technology, and that means the science behind it is new. If you go and look for papers on what the environmental consequences and issues are associated with this, you'll see nothing in the peer review literature as of January 2011. All the literature since then, so it's new. Now this is what the Department of Energy predicts will go on to the future, and I want to say right off the bat, I think they're overly optimistic about how much shale gas is out there or how much could be developed, but it's also overly hyped. If you listen to the president in his campaign speeches or in his State of the Union message, he said more than once that shale gas will make the United States energy independent for 100 years into the future. Well, that's not true, just no way. This is what the Department of Energy says, and I think this is a little too optimistic. But if you look from 2009 up there to 2034, they're saying that the conventional natural gas production is falling off. It's probably going to fall off more rapidly than they say because the resource is probably smaller. They say we'll stop importing gas, and all of our imported gas comes from Canada at the moment, by the way, and that we'll have that made up by shale gas, which will make up a majority of our production out there into the future. We are somewhat on track here towards this development. It's not quite as fast as they were projecting a year or so ago. I don't think that can be sustained. But keep in mind that even under these optimistic conditions, we're not really becoming a larger user of gas in the country. It's a relatively modest change. Overall, it's a 20% growth over that time period. All right, mostly I'm going to talk about what the greenhouse gas footprint of shale gas is, how it compares with other fossil fuels. And I got interested in this because shale gas is widely promoted as a bridge fuel, something that allows society to continue to use fossil fuels and yet have less consequences on global warming, and therefore allow us to go on for 20 or 30 years, whatever it takes, until we become truly sustainable and renewable energy. And the question is that really true in terms of its global consequences? And I just want to say, I started thinking about this because of the global change aspects, and obviously people are now paying attention to global changes. It's from this week's issue of Bloomberg Business Week. So business people are paying attention, and I'm hoping that they'll start to pay attention to the need to really make a change in how we use energy in the society as a whole. Okay, so a greenhouse gas of natural gas generally, and shale gas in particular. Shale gas is just a form of natural gas from shale formations. The reason that industry is able to say that it has lower carbon dioxide emissions compared to other fossil fuels is that, yes, indeed, it has lower carbon dioxide emissions than other fossil fuels. And I don't think anyone would really argue with these numbers. This is the amount of carbon dioxide per energy that's released as heat when you use coal, diesel, oil, or natural gas, and natural gas has lower carbon dioxide emissions. It's a more energy-dense fuel. But that's only part of the story because, of course, methane is, natural gas is methane, 85 to 95% methane. Methane is the second most important greenhouse gas behind current human-driven global warming after carbon dioxide. And it's a much more potent greenhouse gas. I'll go through this a few times in different ways, but even relatively small emissions of methane matter. So we started looking at this in late 2009. I started by going, well, someone must have looked at what the greenhouse gas footprint of this shale gas is. And we searched and no one had, and I asked colleagues and no one had any idea of anyone who'd done it, and it turns out no one had. So there were actually no literature whatsoever on methane emissions or greenhouse gas footprint as of the time we started working on this. And there are really only 3 papers on even conventional natural gas over the previous several decades. They came out in 2002, 5, and 7. So I'll show you some data from that. The Environmental Protection Agency did not separately consider, as of 2009 or 10, shale gas from conventional gas, and they were using some very optimistic assumptions on methane leakages from a study that they did with industry back in 1996. And that's an important part of the story here. So, before I get too far, I should say we came up with a paper, and I'll show you results from that. First paper that we published, and the first paper on the greenhouse gas footprint here, came out April 2011. Other things were happening before our paper came out, and there's a lot of pushback that has come out since. I'd started giving talks on this work in the spring of 2010, so about a year before our paper came out, I was giving public talks like this, and those got picked up on very quickly. And in fact, the White House heard about it, and the White House ordered the EPA and the Department of Energy to check our stuff out. So some of what you'll see is that there's governmental stuff and industry stuff that was going on in the background at the same time as our paper was coming out. What we looked at was the methane leakage and venting, and we looked at this flowback period. That's after you put all that liquid down there to fracture the rock, the liquid flows back to the surface somewhere between a week up to a month, maybe 6 weeks in the outside case. Free-flowing water, and there's a lot of gas associated with that. So we looked at that. There are routine leaks at any gas field over the life of a well at the well site. On average, there are about 150 little pipes and joints and connections, and they leak. There's this process called liquid unloading. I'm not going to go into that unless you really want. Some gas needs to be processed, and there's some leakage associated with that. And then you need to store the gas, because most gas used in the United States is used in the winter. It's mostly for heating. You got to store it. You got to get it to consumers through pipelines and things, and there's leakage associated with that. So we tried to come up with numbers for all of those things. The very first talks I gave in this, every talk I've ever given, I have said that the data we used were of really poor quality, really lousy industry will pick this up and they will repeat back that I've again admitted that we use terrible quality data. So yes, I'm again admitting we use terrible quality data. But we used the best quality data that were out there. And we pulled it together as well as I think anyone could. And then we tried to say what that means, and I'll show you what that means. Our conclusion was that it's scary enough that someone ought to be doing a better job of getting real quality data, which is starting to happen, I'm happy to say. So what did we use? We used peer review publications. There were 3 of those. We used an EPA report. I mentioned previously the EPA was relying on stuff from 1996. They were ordered by the White House in the spring of 2010 to respond to us and see if we're wrong. Their response was to completely relook at how they looked at shale gas and conventional gas. They put out their first report in November 2010 when our paper was still out for review, and we used that in some of our revisions. They've updated a few times since after our paper came out. There's a congressional report from 2010 we used industry reports, and we used a lot of stuff from industry, financial reports, other things. Some of that we got from the EPA. A lot of it was leaked to us by industry insiders, which is interesting. After we started getting some press from our talks and industry started to try and say we're wrong, we also started to get contacted by people who work for industry and saying, you know, it's worse than you think. And they'd send us stuff, and we didn't use it unless we could verify the source and double and triple check it. But that is partly what we used. Just a sense of where the EPA was coming from in their revision. They use an emission factor here, so process by process or valve by valve, compressor by compressor, they come up with a emission rate per volume of gas going through it. This is what they're saying as of 1996. You don't need to pay too much attention here to the detail. This is their update as of November 2010. They're still updating these, so these numbers change. But you can see they went up. They went up a lot. Yeah. So this is what we said in our paper. We looked at the various stages I talked about. The only difference here between conventional natural gas and shale gas in our paper was that at the time of well completion, after you have this massive hydraulic fracturing, this flow back of liquid, we estimated that there was a pretty large release of methane to the atmosphere. The numbers here are all percentage of the lifetime production of a well. So a well might have a production of 3, 5, 7 years. We're saying that in a week or two after it's hydraulically fractured, 1.9% of that total production is emitted to the atmosphere. All of these other numbers are more gradual, and they're all the same for conventional and shale gas. That's not necessarily true, but that's the best we could do at that time with the information we had. So we give a range here for conventional natural gas of 1.7 to 6, and for shale gas of 3.6 to 7.9% of lifetime production of a well. I'll come back and put this in better context later, so I won't go into too much more at the moment. Just to give you a sense of what goes on at the time of hydraulic fracturing, this is a forward-looking infrared video imagery, color enhanced. So this is a video camera that is tuned to look at methane, which of course is invisible to the naked eye. This is color enhanced, so that's not burning, this is methane. It's a cloud of gas coming out at this time of hydraulic return waters. There's more and more information like this. That video is available if anyone wants to look at it online. I can give you the link later. It's pretty cool to look at. So this is our paper, and this is what we've said. And right off the bat, we looked at 2 different time frames. I'll come back to that in just a second. Let's just look at the 20-year time frame for a minute. I'll walk you through it. We looked at shale gas with our low estimate and high estimate of methane emissions, conventional natural gas, low and high, coal that's either surface mined or deep mined, and we looked at diesel oil. And the blue bars are the amount of carbon dioxide that's emitted per megajoule of energy that's released as the energy is burned. And indeed, natural gas, whether shale or conventional, is better that way than is coal or diesel oil. The red bar was pulled together here. This is the indirect carbon dioxide emissions. The energy, the carbon dioxide that's released when you drive the trucks. There's 1,000 trucks of water that goes for each well to be fracked, and there's stuff that's hauled away. And we thought that would be a lot of carbon dioxide. It's really not. Renee Santora, who works for me, spent 6 or 7 very tedious months pulling those numbers together, and it's a boring little sideshow, but we looked at it. And it's a smaller issue than I would have imagined. And the magenta color here is methane. convert it to the equivalence of carbon dioxide. And that's where the time frame comes in. So on this 20-year time frame, we are saying that shale gas has a larger greenhouse gas footprint because of the methane leakage than any other fossil fuels. It's worse than conventional gas, it's worse than coal or diesel oil. Now in the 100-year time frame, that's less so. And the reason for that is that methane is an incredibly potent greenhouse gas. We convert it to a carbon dioxide equivalency using a global warming potential. And that is a time-sensitive issue because when methane's in the atmosphere, it absorbs infrared radiation at wavelengths that carbon dioxide does not, much more effectively. But it's only in the atmosphere for 10, 12 years, or something like that. So over time, its influence gets diminished. Carbon dioxide has a much longer time frame, much longer time frame of concern. We use global warming potentials from work of Drew Shindell from NASA Goddard Space Institute. So we're saying that at a 100-year time frame, methane is 33-fold worse than carbon dioxide in terms of its absorption capacity. It's absorbing 105-fold more radiation at the 20-year time period.
What's built in concerning production during that 100-year time frame?
This is just nothing. So this is a snapshot as of the time of production. So obviously, if there's continuing production, then you're up there somewhere. Yeah. And you know, you'd want to use some sort of dynamic model to do a better job. This is quick and dirty. It's what the literature done before. We followed suit. Okay, this is the 50 people that mattered. Time magazine last year recognized me as one of 50 people that mattered because of our highly controversial paper, they call it. I'm not sure I like having it called controversial, but it's nice to get a little recognition. In the week that our paper came out, it was picked up by 1,200 newspapers right off the bat. Huge interest, huge pushback from industry. And I just want to, for context, these are other people who mattered in 2011. So it's not necessarily a huge honor. So some of those people I respect greatly. It was an honor. How did what we do compare with what others have done or have done since? And a lot of stuff has happened since. Part of the industry public relations campaign is to say that our stuff is way out of line with anything else anyone has ever done or thought about. So let me walk you through that. Looking at conventional natural gas and shale gas here, comparing our stuff with the prior literature. No one had looked at shale gas before us, but for conventional natural gas, our study looks pretty good compared to that paper by Hayhill et al. That's a Department of Energy study from 2002. Their number is right in the middle of our mean. That's our stuff is independently derived. We didn't use their estimates, so that is surprisingly good agreement. Our number is higher than that of Yamarillo et al. There's low relative to Hayhill, but their emissions are based entirely on the EPA 1996 emission stuff, which EPA was already changing and saying was wrong as of November 2010. Well, since April 2011, and this is a little bit out of date, I have not updated this in the last 2 or 3 months, but these are the papers and reports which came out, a massive amount of stuff. You sit there and go, how can people put out so many papers so quickly? Most all of these are responding to our paper. But of course, part of the reason is that they were working on before our paper came out because our paper got press release a year ahead of time. So this stuff is all kind of in the works. And not all of these papers are independent, I will say. Many of them are very critical of us. Some are quite supportive of us, but they're not necessarily independent. You can see cross-working in the assumptions and the plate. The blue of these are peer-reviewed. The black are non-peer-reviewed. I'm going to run you through the peer-reviewed ones where they actually gave estimates of methane emissions, because some of these didn't. For instance, Wigley concluded that yes, shale gas is a really bad idea. They used a dynamic model to get around the global warming potential issue, but he didn't actually estimate methane emissions. He just gave a range of emissions, and so I'm not going to show you that. These are the peer-reviewed papers where people have looked at either shale gas or conventional gas in terms of methane emissions. Entire life cycle from the time of well development to final use. And to make it a little easier, I've color-coded them here. And they're color-coded relative to what EPA was saying as of the late summer of 2011, just over a year ago. So at that point, EPA had come up to those kind of numbers, and you can compare them with ours. Papers are in blue here if they are broadly consistent with EPA. Now, I'm not saying EPA is right or wrong, but EPA has started regulating shale gas based on methane emissions, and those are the numbers they're using to do so. So you can take it not necessarily as truth, but as a good reference point. And blue papers and blue numbers are numbers which broadly are consistent with what EPA is saying. Our stuff is broadly consistent with what EPA is saying. Green means that they are estimating methane emissions higher than what EPA now says, and red means that they're estimating things that are lower. Now, I'm going to run you through just one or two of these and then take another look at this. My take on this, A, there's less variation in these numbers than you would expect when you read the public relations stuff from industry saying we're way out of line. B, I don't think any of these have enough information behind them to say that they're either right or wrong. I really do think we did as good a job as we could with lousy quality data, but there's a need for better quality data, and none of these are based on higher quality data than we used. But just a point or two, Yang et al. Here has one of the lower estimates for shale gas, and I think there's a good reason for that. Their actual estimates of methane emission at the time of well completion and all are a little bit higher than ours. They're not lower at all. But over the life cycle, they end up with a lower emission factor, and that's because they assume that a shale gas well puts out a lot more gas over its lifetime than we do. And these are all normalized to the lifetime production of a well. You with me on that? That's an important point. And for context, there's another paper with an early Department of Energy study saying we're wrong. Also used a very high estimate of lifetime production of a well. And there's a study with David Hughes put out critiquing and comparing our study with the Department of Energy ones. Hughes used to be a geoscientist. He ran the shale gas program for the Canadian government before retiring. And he's been a very helpful, independent looker at things out there. So what he did was look at these bars here are the ultimate recovery of a gas well. And this is what the Department of Energy study said. Don't worry too much about the blue versus red. The point is that the normalized emissions per lifetime production of a well go up as the lifetime production of a well goes down in estimate. So he said a good estimate for lifetime production would be about here. Our estimates of the footprint's about there. What he says is that the Department of Energy methane emissions, if you normalize them to a more realistic lifetime production of a well, look a lot like our stuff. This is what the Department of Energy published. Much more optimistic because there's a lot more gas. Well, that's what Hughes was thinking as a geologist on this, but there are data which have become available since then. And this is from a US Geological Survey study which came out in August of this year, where they're looking at the probabilities of production of individual wells in the different fields of the shale gas plays of the United States, and their mean predictors here of what lifetime production will be. So the higher you are here, the more gas is produced over a lifetime of a well. These are based on real data. And this is the estimate that the Department of Energy and that Yang et al. Study were using in terms of production. They're way, way too optimistic. There are no shale gas fields in the United States that produce gas at that rate. So that's an important assumption in here, and I think it makes our stuff look pretty good. Here's another study. This came out of the Department of Energy. They are one of the few studies which says there's actually less methane emission from shale gas than from conventional natural gas. Almost all other studies say the opposite. And they said so for two reasons. One is they say that there are no emissions at the time a well is completed, of the sort that I've argued occurs. The other is that this process of liquid unloading, if you build up fluids in a well, you have to blow those out or do something else to maintain productivity of a well. They say that happens only in conventional gas wells, not in shale gas wells. That's just dead wrong. In fact, it happens more frequently in shale gas wells. And they also made a arithmetic error, which I won't go into here. But anyway, the numbers aren't particularly good. Let me run this by you one other way, and then I'll get on to a couple of other issues. Here, this is a background paper that we wrote for the National Climate Assessment back in February. I and the co-authors of our original paper joined with Drew Shindell of NASA Goddard Space Institute and a few other people to try and synthesize all of this information for the climate assessment. And here we're breaking it out. These are percent emissions again over the lifetime of a well. We're breaking up into what happens at the well site for conventional gas. We'll look at shale gas, and then we'll look at the downstream storage and emission. So these are the various published estimates in the peer-reviewed literature for what happens at the well site for conventional gas. Our numbers and EPA's are about the same. EPA is a little bit higher now. Most of the other numbers are similar. The Department of Energy number there is the highest, but they made a 30% mathematical error, so that number should be reduced by 30% using their own data. That's a industry study where they didn't really document why they think it's so low. This is by Professor Cathos, who's a colleague of mine at Cornell, who has spent the last year and a half going around saying, I've made this all up, and he's very critical. He has a lower number. And if you look at his paper, he says it should be half of what EPA said because EPA was too high. But he doesn't say more than that. So anyway, that's the range. Unconventional gas, shale gas, here largely. There's also some tight sand formations which are not shale gas but use a similar technology to get at the gas. Again, a pretty large range. Our numbers are right in line with what EPA is thinking. My friend Professor Cathos again has a low number. The industry number is a little bit lower. The thing to note here is that this paper, Patron et al., is the only number in here that is based on actual integrated field measurements. And this paper came out in the spring of this year. They made atmospheric measurements in a gas play in Colorado over a year. And they come up with an estimate of 4% leakage. More than we used in our paper, more than EPA says, more than anyone else. And that, unlike all of the lousy quality data that went into our study and all the other studies, this is quality data. It's a real measurement in the field. And we need more of that sort of thing. If we look at the downstream storage, the pipeline distribution, high pressure pipelines and distribution into consumers, here we are way out of line compared to EPA and others, and I want to emphasize that. There are these three studies. These are all based chronologically, by the way, of date of publication. So our stuff is quite consistent with what went before us. Again, it's very similar to the Department of Energy study from 10 years ago. That's coincidence, so we didn't use their number. It compares favorably with this. That's not coincidence because we gave a range and our low end number is based on their number. But there are a bunch of reasons why we thought they were too low. I can go into that detail if you like. So we gave a range and our mean happens to, by coincidence, be there. EPA says less. This is the sole number that they have not yet increased since their 1996 report. They're still working on it. And I'll be amazed if this number doesn't go up. All of these other numbers are based on derivatives of the EPA. It's not independent data. The only actual measurement in all of this is in this paper. But I just want to point out that there is leakage in distribution systems, and this is work of Nathan Phillips from Boston University. This is Boston. He's driving around with a Picaro instrument measuring methane on the streets, and the peak height here is proportional to the methane concentration. He's looked at the stable carbon isotopic composition. This is natural gas. Each of those is an individual leak. And they have a paper that's been submitted for publication to put the flux number on this. And I haven't seen the final paper, but I've been told informally that it makes our stuff look like we're way too optimistic. Things are worse than we thought. I also want to emphasize that the distribution system in a city like Boston, or in fact most places, is pretty old. I mean, a lot of it's cast iron pipe that's butted end to end, never welded, had seals in it when they put it down in 1918, but no one's done much maintenance on these things. If they get a massive leak, they got to fix it, but small leaks they don't because it's not cost effective to do so. The high pressure pipelines, they are under more pressure to try and, pipelines are under more pressure. Industry's under more pressure to try and minimize the leaks because when things go bad, they go really bad, and there was a massive explosion here just over 2 years ago in the San Francisco Bay Area. But half of these high pressure long distance pipelines in the United States are 50 years old or older. It's old stuff, so there's issues associated with Now I want to just very briefly show you this, because I really think there's a need for more higher quality data, the sort that Patron have done in Colorado. This is some work that I've been involved in personally. We haven't yet submitted this, but we hope to soon. And the real leader of this is Paul Shepson, who's an analytical chemist at Purdue, as well as a pilot. So he flew this airplane in collaboration with us at Cornell and a group at Penn State. And he flew on a track of about 2,000 square kilometers in southwestern Pennsylvania, where we thought there might be a lot of active gas development and exploration underway. This shows the hotter the color, the more methane in the atmosphere on average as he flew around, so we're seeing some spatial patterning. And this shows you a particular track he took. So we're looking at increased altitude here by latitude and longitude. What he's doing is actively looking for a peak of methane. He's not randomly flying around. He's going over rigs, and when he sees a peak, then he flies these sort of spiral patterns, and he goes up so we can visualize a plume. And you can spatially average that, as he's done here for one of these wells, and from this we can get a flux estimate. And the take-home messages are two. When we try to estimate what the methane leakage from this 2,000 square kilometer area should be using the emission factors we published in our paper, we're seeing more methane in the atmosphere than we could account for. There are about 4,000 gas wells in that area. There's also some coal mining, so there's plenty of room for uncertainty in things. Most of those wells do not show a particularly high peak of the sort I'm showing you here, but some 40 of them do, so 40 out of 4,000. And the emission rate that we are characterizing from this one well we're calling delta, and it's characteristic of about 40 of these wells, is far, far higher than anything we estimated in our paper. Far higher. So there are a series of problematic wells, and we're trying to figure out what's going on there. So more and more people are doing this new field measurements, which is really what's needed. I've heard of some other papers which are coming along, and I'm told that by and large, almost everything is showing we were pretty conservative in what we published, and things in fact look that bad or worse. But in the meanwhile, I think our estimates are still as good as anyone's. Now, there are a couple of other points that are critical here. One is the time frame. I mentioned the 20-year versus 100-year, and maybe we should be looking continuously. We did the 20-year and 100-year because the IPCC has given global warming potential estimates for those two time frames, and because the work of Shale et al. Also gave global warming potentials for those two snapshots in time. That's why we did it. It's also what the prior paper did. So again, looking at the various papers here, these are chronologically ordered down. The black ones are people who chose to look just at the 100-year time frame, and blue are those who looked either at continually over time or 20 and 100 years, as we did. A lot of these papers only look at 100 years. Most of the papers that only looked at 100 years are pretty critical of us. Some of them say it's inappropriate to look at a shorter time frame than 100 years. And if you press them on that, and read the press reports, the reason for that is that the Kyoto Protocol specifies for international accounting that methane be compared with carbon dioxide on a 100-year time frame. That's fine. Kyoto Protocol stresses that. But that does not mean that what happens at shorter time frames is unimportant. And my worry is the possibility of tipping points. This is a kind of a nice paper, if you haven't seen it. It's a summary of how the average American citizen looks at climate change, whether climate change will be gradual, or whether we live in this incredibly fragile world that could go to hell overnight, or whether no matter what you do, things are always going to be stable. This is the threshold response, which of course is what climate change scientists think. We're in sort of a stable period, but if you force things enough, you'll force it into some alternate climate system past some tipping point. Surprisingly, 35% of adult Americans correctly predict that's the way the climate change system. Most don't, but that's a higher percentage than I would have thought. That's an aside. But anyway, tipping points. And one of the tipping points is what Jim Hansen has suggested, that we start melting methane hydrates and clathrates if we reach an average warming of 1.8 degrees Celsius above the long-term climatic average. Of course, then you get a big natural quotes flux of methane, and that would not be a good idea. So this came out after our paper, and it's another paper by Drew Shindell, came out in last January. It's a similar thing which came out in the summer of 2011 from the United Nations, World Meteorological Organization, and UNEP. But I think this is an important paper, so let me give a few minutes to this. If we look at 1900 up to the future 2060, and we look at the average temperature of the Earth, this is the historical temperature record up to 2010, and then 4 projections into the future. The IPCC reference date from the IPCC 2007 synthesis report. That's if society doesn't really come to grips with trying to control greenhouse gas emissions much. And if so, we will reach a threshold of 1.5 degree warming by about 18 years from now. And we'll reach a threshold of 2 degree warming by about 35 years from now. Those are dangerous temperatures in terms of the Hansen idea for a methane tipping point, and probably in terms of some other tipping points. These other 4 lines, what are they? This one here is if society began last year globally to take on aggressive carbon dioxide controls, but did not worry about the shorter-lived greenhouse gas emissions like methane. And there's enough lag in the climate system that even though you start to control here, the plant's still going to warm dangerously. This one is if you ignore carbon dioxide, but you instead control methane and soot like carbon. And that has a much more immediate effect. It keeps us cooler for quite some time into the future. If you control everything, then you're here. Clearly you want to control everything. But controlling methane is important. And controlling methane on short time frames is important if you're worried about tipping points. And so in our original paper, we gave equal weight to the 20-year and 100-year scenario time frames, but I'm more and more convinced that the 20 years is pretty critical. And at the 20-year time period, keeping in mind that our estimates of methane emissions are probably conservative, it's probably worse than this looks. So shale gas is probably a really bad idea thematically. A couple of other things just for perspective here. These are data from the U.S. Environmental Protection Agency. These are not our data. This is where the United States Protection Agency, as of the spring of 2011, was saying methane emissions from the United States comes from. Natural gas industry is the #1 source. I think it's probably worse than that. If we look at the National Greenhouse Gas Inventory, and look just at the 100-year integrated time frame, and we update using modern global warming potentials, which the Environmental Protection Agency does not do because they've been told to use the Kyoto Protocol numbers from decades ago. The 100 time frame, again using EPA estimates, methane's making up 20% of the greenhouse gas inventory of the United States, all sources, 100-year time frame, 44% at the 20-year. Methane is a big part of the greenhouse gas footprint of the United States. And the methane from natural gas is making up 17% of the entire greenhouse gas inventory of the United States. And again, it's probably low because I think the methane emissions are higher than that. Now, another side point, one of the more serious criticisms that's been levied against our work is that we compared greenhouse gas emissions across fuels in terms of the normalized to the amount of energy released as the fuel is burned in terms of heat. And the criticism is we should have just been looking at electricity generation because what people really want to do is displace coal with natural gas to make electricity, which is fine. If you look at the comparison just in terms of electricity generation, then it looks better than what I showed. Natural gas is still worse than coal in time frames up to 50 to 60 years, but at 100 time frame it becomes more better than coal. And the reason for that is that natural gas-fired electric power plants are more efficient than coal-fired electric power plants. We said that in the paper, but it was a little side note, and so we're criticized for not making a bigger deal about it. I want to point out, though, this shows the use over time and projected into the future of natural gas in the United States. Electricity production is 30%. It's been 30% for decades. The Department of Energy predicts it'll be 30% going into the future. Heat is the major use of natural gas, and that's what we focused on for our analysis. I think it's appropriate. And one other way to look at that is we look for 2010 and where the energy supply of the United States is coming from. And and natural gas is providing 25% of the total energy picture. And then we looked at the greenhouse gas proportion of the national greenhouse gas inventory from the total energy sector using the 20-year time frame. Natural gas is making up 40%. So natural gas is not the major fossil fuel in terms of energy supply, but it is if you take this 20-year time frame in terms of the greenhouse gas footprint. And this is for all uses of all forms of fossil fuel. So natural gas is not good for global warming, bottom line. How am I doing for time? Probably wrap it up in 5 minutes or so? 10 minutes, okay. Can the methane emissions be reduced? And the answer is clearly yes. Yes, absolutely they can. I have a lot of faith in engineers. Engineers do incredible things, including that directional drilling, getting that gas out of shale formations. That's amazing technology. So engineers can do a lot of things if we have the right motivation. The question is, should we be doing it? A lot of the leakage now, we talk about, I just used the word leakage. I should be using the word emissions. A lot of what's going on is not leakage, it's purposeful venting. What happens at the time of a well completion is venting. It can be stopped. Actually, regulations that went into force 3 weeks ago are starting to stop it, so there's good progress there. But if you look at a pipeline, they use compressors to repressurize it along the way. The compressors they use, they have two choices. They can use those which have no venting at all, or they can have those which do vent it as part of the normal operation of the compressor. And the latter purposeful venting type are the norm in the industry because they're cheaper. It's cheaper to blow the gas off and use a cheaper compressor. So there's economic decision there. Old stuff, we really want to rebuild the infrastructure of New York City and Boston with pipelines if we're looking at a 10 or 20-year transition away from gas anyway. And it requires regulation. And I've mentioned EPA is now required that venting that occurs at a time of well completion had to stop as of October 15th of this year. They won't require that you capture the gas and take it to market until January 2015 because industry protested it would be too expensive, but now they have to burn it, flare it, as of right now. And that's great if it can really be enforced. I'm doubtful. And question the answer, I can explain why I don't think it's necessarily going to be that enforced. One final point, and we'll wrap up. This is peripheral to what I've been saying, but I think it's important to convey. And that is that there's probably a lot less of this resource out there than anyone listening to the president or to industry thinks. And I'm relying on several sources here, but I particularly want to thank Arthur Berman for this work. He's an industry insider. He's in the gas industry, and he's a very thoughtful person. So he's done several things. This is from a talk he gave back in the spring. But he's looking in detail here at one of the shale plays, one of the fields, Haynesville in the south. And that's a major part of the shale gas production that's gone on to date is in the Haynesville. And what he is showing, this shows over time from January 2008 to the present, well, January 2012, so it's a little bit out of date. Two things here. Here's the number of producing wells in that formation. They've continued to put more wells into production. So keep in mind that most of the gas from an individual well comes out of the ground in the first year. These things fall off quickly in time. So you need to keep putting wells out there to get gas. This is the rate of production from the field. It's leveled off despite the fact that more wells are being drilled. Now that's worrisome if you think through what it means. One of the things it means is it gets a lot more expensive to produce the gas. So this is the January 2008 to June 2010 versus July 2010 to September 2011, the total cost of getting that production out. It's becoming more expensive to get the gas out because they need more and more wells that aren't producing as much gas per well. And another way to look at that is if you look at their cash flow for the Haynesville, on average, all the companies drilling there, in what has been the largest gas play so far of shale formations anywhere in the world, from 2005 up to the end of 2011, there are two lines here. This is the cash that industry is making by selling the gas to market. And that goes up and down both because production is going up and down, but because the price of gas is. As of today, the price of gas is about $3.15 per 1,000 cubic feet. 2 months ago, it was $2.65. 4 years ago, it was $12. So it bounces around a lot. This is the cost that they've put into getting the gas out of there. And that's gone up for the reason I just said. The wells are becoming less productive. They've played out the most productive ones already. And so they were making a net profit here. They've been losing a net profit for the last several years there. So they are, and that's true of all shale gas plays in the United States. Industry is losing money. They've been losing money. They cannot profitably produce gas at the price of natural gas as it is. But the other thing to look at here is that the cost line there is going up. And it's gone up to a point now where it's higher than they were ever making money, even when the price of natural gas is up there. So you play these things out. The current price of gas, just over $3 per 1,000 cubic feet. In order for this to be a sustained economic industry, the price of gas has to go back up to $12 or something. That's expensive gas. One other thing to look at is how much gas is really there regardless of economics. And this is one of the first estimates, Terry Ungelder from Penn State, looking just at the Marcellus Shale here, our New York and Pennsylvania, Ohio Shale. He gave a pretty high estimate of how much is technically recoverable there regardless of economics. Department of Energy in 2011 said, no, he's a little too optimistic, it's more like this. I'm showing you the Marcellus because this is the only place where people have done a really good comparison so far. But in this report from 2011, the Department of Energy said that this made up more than half of the entire shale gas reserve of the United States, 55%. So this is non-trivial. And they used the same methodology here as they used everywhere else in the country, and in fact everywhere else in the world. And if you've ever seen a shale gas map of how much shale gas is in Europe, et cetera, it's the US Department of Energy that did that, using the protocol they used here. The US Geological Survey came out after this and said, no, it's 5-fold lower. That's the technically recoverable resource regardless of cost. So there's probably less gas there than the Department of Energy said. The Department of Energy agreed with that. They reduced their thing. The president in the State of the Union message was still using this resource and inflating it massively. There's probably less gas. And this is a busy slide, so let me just give you the bottom line. This is an industry-based best estimate of how much gas is economically recoverable, including prices way up in the $10 to $12 per 1,000 cubic feet, including conventional gas and shale gas for the entire United States. Our current rate of consumption, we have about a 23-year supply, according to industry sources. Not 100 years, not replacing oil, and not if we export it, and not if we use it as a transportation fuel. So, let me just leave you with a counter view, and I'll quit. Mark Jacobson from Stanford has been pushing the fact that he believes we can go to a truly fossil fuel free based energy in the United States by 2030 or so, totally solar, wind type based. He and others, I'm a minor part of it, but have produced a plan for New York, which makes the same sort of argument with some fairly concrete details about it. He convinced me enough that I went and bought an electric car in the spring. It's great fun. Even in Ithaca, New York, it works for me. I love it. So my conclusions. Shale gas, if it's continued, will aggravate global warming. It also distracts politicians and the public from what's needed. If the president is out there saying we have a 100-year supply of gas, we're in trouble, you know? And he is, and we don't. It also takes a lot of capital. If you're going to talk about really trying to reduce these methane emissions and rebuilding infrastructure, pipelines and all, it's a huge investment in capital. I would argue we should be putting it into smart grids and moving into the 21st century finally. And I haven't got into the local pollution, but there's an awful lot of local air pollution, local water pollution associated with this as well. So, a lot of people part of this work, and I want to acknowledge that. And Cornell University has been surprisingly supportive economically and otherwise of our work, so I'd like to acknowledge that. So, thank you for listening. Yes?
A question. It's known that fracking can cause small earthquakes locally. I'm wondering if these mini earthquakes can contribute to an extra venting of methane. What do you think about that?
The question is, fracking causes local earthquakes, would that increase the methane formation? Let me give you a two-part answer. First, there is no evidence that I have seen that fracking causes local earthquakes where the fracking occurs. When you take the frac return water and you try to do something with it, a lot of what they've done is to inject it into deep disposal wells, and there's excellent evidence that that has increased earthquakes at the disposal well sites, but not at the site of formation. Probably is therefore not increasing the methane flux. But there's also pretty good evidence accumulating that as you frac, you are contaminating surface aquifers with methane, you're opening up little fissures and things. No one has yet estimated how much methane that is. And it's not included in our analysis. It would show up in the regional airplane flyover I did, which, as I say, showed more methane than we would have predicted from our stuff. And that might be one of the reasons why. Could be other reasons.
Your analysis also doesn't include all the carbon footprint of, say, the trucks that have.
No, actually it does.
That does.
The
Okay.
question is, did we include the carbon footprint of the trucks and all that? That little tiny, if you remember, I had a blue bar of the direct emissions of carbon dioxide and big magenta methane normalized carbon dioxide. There's a little tiny red bar in between. Those are the indirect emissions from the trucks and from building pipelines and all. We're pretty conservative. I could easily believe that bar might be twice as big as it is, but it's still pretty damn small. And I'm surprised because it's an awful lot of trucking and this and that, but it just shows you how large the other footprints are, particularly the methane leakage is what it really shows you.
So what's the governor gonna decide, having postponed the decision on?
Well, I don't know. You know, if you're following it closely, the state DEC put out a supplemental draft generic environmental impact statement in 2009, and they got thousands of comments, and they took their time to redo it, and they issued a new report in 2011. And I'm told they got 10,000 comments on that. They are still working on those comments. It's clear that political decision in the end. A lot of people thought the governor would issue permission for, say, 75 well development in the southern tier of New York as of last summer. He got a lot of political pushback saying that's kind of, you know, is it okay to make the southern tier Binghamton area a sacrificial zone for the state? And then they backed off of that. NRDC, which had been working with the governor behind the scenes to sort of push that through as a compromise, backed off and said they had never said such a thing, which is not true. They demonstrably did. It's in their comments on the Yes Guys. I think the governor is finding, he's searching, I'm sure he's searching for some way to move forward that will have the least political damage for him. And I don't think he's yet figured out what that is. Which, if this is an issue you care about, tell him you care about it. That will help.
100% of the grassroots objection is about potential contamination of groundwater, right?
No, the question is 100% of the ground roots is about groundwater contamination, and there are reasons to be concerned about the groundwater. Tony Ingraffia, who's my colleague here, is an engineer, has pulled together the state of Pennsylvania DEP data, and he shows that there's about a 5 to 6% initial failure rate in the cementing jobs around wells. So there's contamination associated with that. They haven't worked through what to do with the frac fluids when they come out, the disposal issues causing contamination. That's clear. But there are other issues as well. There's local air pollution. These things are emitting benzene at the same time they're emitting methane. If you look at the state of Texas data, at times the air benzene levels are getting up to acute toxicity levels. I would be concerned about that. A lot of people are just concerned about what it means to their community, and sort of boom bust, and taking a small rural area and boom bust economy is not what they want. So there's that aspect as well. But when I started working this greenhouse gas footprint, I got a lot of people saying, "Why do you care about that? It's all about water quality." I said, well, I'm a scientist. I care about what I care about. I'm curious to know what the greenhouse gas footprint is. But our work has had an influence. And the example I'll give you is the Sierra Club, which had said, yes, shale gas makes sense as a transitional bridge fuel despite the local problems, which we'll try to take care of, reversed themselves as of last April. And they now are opposed to shale gas development anywhere in the United States because of its greenhouse gas consequences.
Your comments about NRDC and Sierra Club are interesting because This university, we've had very close ties with the Environmental Defence Fund. EDF had its genesis right here
Right.
in this department. So they have come out with a guarded yes, that proper safeguards are taken, which kind of shocked me and makes me wonder whether they've lost their way a bit. But now, didn't Cuomo sort of delay the decision by ordering a health-related study to be done?
Yes, couple of questions there. He has asked, well, originally, there's a lot of demand for a health study because the new supplemental draft generic environmental statement, which came out September 2011, did a lousy job with health stuff. And so a lot of people said you got to do a better job with health stuff. A lot of people are calling for a fully independent analysis. What the governor said in the end was that his Department of Health would do a review of what the DEC had done. And that hasn't yet been done. So there's some interplay between the departments. But it's not outside of government yet. He is waiting for that, but that could come through at any moment. So who knows how long a delay that is. On Environmental Defense Fund, they are, I think, the most pro shale gas of any of the big environmental groups out there so far. They seem pretty heavily invested in saying it can be done safely. We're going to try and help make it be done safely. And I hear you about your connection in this university. I have a personal connection from the two. As Bob said, I worked at Cornell since 1985, but from 2000 to 2002, I took a 2-year leave of absence, and I worked for Environmental Defense Fund. And this is being recorded, and it's going to go over the web. But let me just say that I'm disappointed in how Environmental Defense Fund has handled this so far.
I have a question, I guess a question and a comment maybe, but the slide that you showed from the industry consultant was really kind of striking, you know, and showing that basically for these, you know, energy companies and for these gas companies, it's not going to be profitable in the long term. Do you foresee possibly that, you know, there could be some subsidies given just to, I guess, fulfill this problem, that we're fulfill the promise that we're going to use this as a transition fuel? And
yeah, no, that's an excellent question. Yes, I mean, one of the things I glossed over, I could have spent a little bit more time with, is that industry has been pushing hard. I'll give you one example. Industry's been pushing hard to use natural gas as a transportation fuel, long distance trucking transportation. They have endorsement from the senior leadership in both the House of Representatives and the Senate from that. The president has stated he thinks it's a good idea, and they've talked about subsidizing the transition because it requires a lot of infrastructure to make that happen. And the industry is definitely asking for a subsidy to do that. If you increase that use of the gas, obviously it's going to drive the price up. It's also going to take the optimistic 20 years to supply and make it less than that. Industry is also very interested in exporting the gas, because although the price here is down in the $2, $3, below $4 range for the last 4 years now, in Japan right now it's about $16, $17. And in China it's about 14, I think, at the moment, and in Europe it's about 11 or 12 at the moment. So clearly, if you could get the gas to those foreign markets, you'd make a lot more money. Oil has a truly global price, and it moves all over the place. Natural gas historically doesn't. It's sort of a regionally priced thing. So part of the vision of industry is to internationalize that, move it, and I don't think they're going to be able to do that economically without some subsidy, but that could be done in the name of, you know, national security and home security, energy and things. Yes?
Ben Chu is a pretty smart guy running
Yeah.
the energy department. How come they're still sort of far behind on their numbers and the recognition of what you see as a problem?
Well, I agree with you. Ben Chu's obviously a very, very bright person and a very thoughtful person as well. I've never met him, but I'm impressed by him as a thoughtful person. He runs a big, complicated agency, and there's all sorts of complicated politics involved in the whole thing. And a lot of this is new. Our paper was just published April 2011. That's a year and a half ago. That's not very long ago in the life of a bureaucracy. The president was solidly invested in the idea of making shale gas part of his re-election strategy as of that time. That's very clear. I've been told by that by insiders in EPA, DOE, and in the White House. And so those agencies clearly were feeling some pressure not to be too vocal about this through the election time. I will be very interested in seeing what happens now. And I'm cautiously optimistic that science will start to come into play more than it has so far.
Worst case scenario, suppose all the shale fuels get used in the next 25 years to set the supply. What's the net contribution over a 50-year time scale or so to methane and greenhouse gas emissions globally?
Well, those are U.S. numbers I gave you. So, currently, the United States is producing about 28% of the national gas. If you look at global methane inventory emission numbers, everyone in the world is using EPA emission estimates. All other countries use U.S. EPA emission numbers because that's what the IPCC did. They're still using the old ones. So just as an aside, if you look at anyone's inventories out there, it's using the old 1996 EPA stuff globally. So you'd have to recalculate that through and see if it's going to play out the same way. But currently, 28% of the natural gas production in the United States is coming from, 28% global production comes from the United States. A little over 30% of that is now coming from shale gas. You start extrapolating that out, and it's not regulated to cut down the initial emissions. You would increase the methane fluxes from the natural gas industry by about 30%, 40%. That would have a measurable increase in the atmosphere. I'm sorry, where'd you point?
No.
I'll let him point. I don't have my glasses, I can't see back there, I'm sorry.
So you mentioned that, there are plans, in regards to what you were saying, how, it's not profitable at the price of gas right now for these companies to be, extrapolating the shale gas, but if they were to export it to, let's say, Japan, they could maybe make profit. How do you foresee, if that's the scenario, how do you foresee the increase in, escape methane emissions if you're now transporting this gas from New York to?
Yeah, that's an excellent question. I mean, you have to have more emissions when you transport it, right? There has to be leakage. No one has analyzed what that is. There are no primary data that I've seen on it. There's nothing published. There's one or two papers. Actually, some folks from the Environmental Defense Fund put out a paper this past summer which compared some of these other scenarios. They looked at the transportation fuel versus use for versus electricity generation, and they made an argument that transportation was pretty bad just because of the inherent inefficiencies of the combustion in an engine. They did not allow for more methane emissions from fueling and refueling in the transportation. There's one other paper out of Carnegie Mellon where they looked at the export question, but they assumed that the methane emissions would be the same, and they can't be. Tanks vent when you store and move things around, but there are no primary data on that I've seen, and no one even talks about it in the literature.
One more question now.
Thank you. Hypothetical situation. Now that Obama is elected again, you meet him in the White House and you meet the Nobel Prize winner. What do you tell them? What is your advice, given the science that has been happening recently?
Well, I tell them the same thing I just told you.
But they want to hear a very quick story. What is the advice?
Yeah. Well, I had 65 seconds with Lisa Jackson, who's the head of the EPA, 11 months ago. So what I told her was, thanks for your EPA staff for getting on top of these numbers and updating for the first time in 1996. So they've confirmed our analysis that things look pretty bad. There's new science coming along, it looks even worse. By the way, the U.S. Geological Survey has shown that the resource is far lower. Given these issues and given the cost of doing it right, don't you think we should move to renewable energies, to a smart grid? It's the 21st century. That's what I said to Lisa Jackson, and she said, yeah. She also said that the president agreed with me.
Good. Thank you.
These are very sobering types of issues to address, and they're one of the reasons that I think our undergraduate educational curriculum should be centered around these kinds of system-oriented analyses and the implications to our whole social structure, as opposed to the ancient curricula basis that we have now and are essentially going to renew in our new curriculum program here. So I think these kinds of things you're talking about are unbelievably important for all of us, and it's great that you have taken them on in such a forthright and analytical manner, and thank you for presenting them to us, and we'll retire for lunch for some of those who would like to continue this discussion. Thank you, Bob.
Thank you for coming.